All right, everyone, Mr. Graham here. Today, I just want to give you a little bit of insight into how the derivative can actually work, not just in normal y versus x graphs, but in actual motion graphs and kinematics. And to give you a feel for that, I have a simulation set up, and it's through Algodo. If you had me last year, you know that Algodo is a program that we can actually, have motion graphs being plotted for an actual object that is undergoing, in this case, constant accelerated motion, uniformly accelerated motion. So when I hit play here, this object, this box is just going to slide down the ramp. I have turned the friction off. If you can see here, you can actually change the friction both on the object and the surface over which it's sliding. So I've turned the friction off, so we don't have to worry about any coefficients of friction here. And when I hit play, the position versus time graph will be plotted, as you'll see. And so there we go. And it is what we expect. We have a parabola, a half a parabola, because it did start from rest. And so what I like to think of, remember the derivative just tells you the slope of a curved line at a single point. And so in this case, the curved line, it's a parabola. And when I think of the derivative, I think of the slope of the tangent line. And if I go along the curve, then that tangent line slope will change. And what's cool about Algodo is that it'll actually show you that tangent line, and you see the dy dx right there, which actually tells you what the derivative at that point is. And so as I go along the graph, see that tangent line changing its slope. It's always touching the curve at one point and 1 point only. And that, ignore the area there, that'll be the integral. We'll learn about that later. That's another calculus operation that we'll have to learn about. But in this case, just think about the derivative, that dy dx. Notice that it is changing. It's getting steeper and steeper. And notice the units on the derivative here. It's in meters per second. If you look at that, dy dx equals at this point 6.003 meters per second. Again, that just tells you the slope. The derivative, the most basic idea behind the derivative is that it tells you the slope of a curved line, and it could be a straight line, but a straight line slope isn't going to change. But it tells you the slope of a curved line at any point on that curved line. And it does change. That's why the derivative is itself a function where you have to plug in a particular x value. In this case, that x value would be about 1. You can see it right there, about x equals 1.02 seconds. So you would plug that into the derivative function, and it would tell you dy dx, or the slope, or the velocity at that point, which in this case is 2.491 meters per second. So when I think about the derivative, as I go along a curve, I just think of the slope of that curve at that point, and it changes as you go across. You can think of like taking a straight edge and just kind of tracing along the curve as you go across. And so hopefully that gives just a little more insight into the derivative and how it can actually apply to motion graphs, because that's where we're headed next. That's about all for this real simple video. Stay tuned for some more robust videos that'll explain this in a little more detail and allow us to actually do some kinematics that we couldn't do last year. And that's about it for now.